great. Yeah, thank you so much. Today I'm going to present a recent work, which is called Zero Knowledge Location Privacy via Accurate Floating Point SNARKs. This is joint work with Chengru, Luca, Philip, who's also in the audience, and Sebastian. And this work was actually accepted next year at S&P, so very happy to present it already here at ZK Summit. Great. So to kick off a little bit with motivation, what we have these days is a lot of location-based services. So, for example, probably everybody that is in this room has something similar to Tile or AirTag enabled, or uses their smartphone in some kind of like geolocation-enhanced way. Which means that the location data that you kind of present of yourself every single day is used either in open source data sets, such as, for example, on the right you can see OpenCell ID, which is essentially mapping the wireless data coverage on a map based on voluntarily submitted GPS data, as well as kind of like measurement data, or an OpenStreetMap, which some of you might also be familiar with. Similarly, it's also used for spatial data processing. For example, Uber uses it to plan their rides. Airbnb uses it to recommend prices. And there's also marketplaces to sell geospatial data. So as you can see, there's a lot of demand for geospatial data. On the other hand, this is also problematic because frequently there's data breaches, and privacy enhancement or obfuscation of data set is not always enough, right? So in 2014, there was, for example, this very interesting data leak where supposedly anonymized data set for taxi data, so rides, historical rides with kind of like destinations and origins, as well as ride fares, were revealed. Essentially, they used an MD5 hash of the identification number of the taxi, which was easily reversed in around 3 minutes per record, and which then revealed by mapping it or the data of the identification number of the taxi with paparazzi photos to reveal which celebrity visited which strip club or gave no tip at all, right? So this is a series of concerns. So the actual question that this raises is, can we actually develop a mechanism that provides location obfuscation, very strong obfuscation, location obfuscation, without ever disclosing the actual location in the first place, right? So ideally, we would like to have a non-interactive proof that proves that I'm in a certain location, where the input is the latitude and longitude, and the output is something else that kind of like obfuscates this location. So what would be good here? So our idea was there's a lot of algorithms already that do geometric mapping onto the sphere of the Earth. For example, the Uber H3 algorithm, which is a hexagonal geospatial index. Hexagons have established themselves to be very useful in this use case, as they have a very good symmetry and equidistant centers, which allows for an ease of performing certain calculations, such as, for example, ride fares in the Uber case. And Uber has this interesting software library where you have an index that is assigned to each of the hexagons, and you have a varying resolution, right? So you essentially have a mapping of the hexagons of the round sphere of the Earth, and the hexagons can be scaled from like 1 square meter to around 4 million square kilometers, right? Which makes this very interesting, as it allows for variable privacy in the protocol that we're trying to design here as well. Good. Now the next question is, if we have this point as a latitude and longitude are usually numbers that are separated by comma, so they can either be represented as fixed point or floating point numbers. The question is, what happens if we get to the boundary of a specific hexagon, especially with very, very high resolution, or very kind of like, which is equivalent to a very small hexagon? The problem here becomes that if you're very close to a boundary and you don't have sufficient accuracy, you end up basically proving that you're in the boundary, in the hexagon next to it, which is equivalent to a soundness error, right? So this is basically the motivation why we also want to do floating point computation. So we want to represent the latitude and longitude in circuits as floating point numbers and do computations on them to prove that you're basically in a certain hexagon. So this is essentially the problem setting. Here on the bottom you can also see this is the experiment that you will see later in the evaluation. So red is, for example, the number is the point that we want to prove. In our experiment, we logarithmically approach the boundary of the actual hexagon. And then on top, we design an application which we call peer-to-peer proximity tracing, where you have another member, which is PU in this case. And PU can calculate the minimal distance to the boundary, the closest point on the boundary of the hexagon in plane, and the total number, the total runtime that you have for U in this case is the verification of the proof and the computation on the boundary in plane. Yeah. Great. So a quick show of hands, how many people here know about floating point and know about the actual representation of floating point? Great. Roughly a little bit more than half. It was more than the last time when I asked. 0.501356. Great. Good. So let me give you a brief overview of this. A floating point number is usually represented as a sequence of bits, where you have always one sign bit, which indicates if you have a positive or a negative number. You have an exponent E. E is for single precision floating point 8, for double precision floating point 11, and you have a mantissa M, which is 23 for single precision floating point and 52 for double precision floating point. And what you see on the bottom here, the alpha, is the actual real, the representation of the real number once you take all those bits and assign them basically to the values that you have. So you can see the exponents determines the range of the number, and the mantissa essentially the precision after the comma. And the sign bit should be self-explanatory, right? Good. So why is in this case fixed point less than floating point, or a floating point better than fixed point? I can make like a very rough comparison here. So if you have a fixed point number with 16 bits on the whole number and 16 bits on the fractional side, as you can see here in the example, which encodes 45.16, you can represent a total number range of plus minus 32,000 something with a precision of up to whatever that number says here. So you can see you have a total of 32 bits. If you take, for example, FP16, so floating point 16, which has one sign bit, 5 exponent bits, and then the rest are mantissa bits, you can represent values that are a lot smaller and a lot larger at the same time, which is fairly beneficial, right? And this encodes, in this case, the same number, but you only have half the number of bits assigned as you would need for the fixed point case. And some of these things can also lead to very detrimental effects. If you use numbers of precision that is not high enough, this can lead to arithmetic errors, such as in this case with the Ariane rocket in, I think it was the 70s, where casting an integer, casting a floating point value of 64 bits to an integer, unsigned integer of 16 bits, led to an exception and led to the rocket explode, which was very expensive. Yeah, so we ideally want to avoid that. So let me tell you how floating point arithmetic actually works, and then successively tell you how we actually encode this in circuit. Okay, so here you can see essentially addition, subtraction, multiplication, and division. So for addition, what you do is you have alpha and beta are two real numbers, right? So you take, for addition, you take the maximum of the exponent, and then you have the mantissa. For the mantissa, you add or subtract the mantissas if you do want to do addition or subtraction. Similarly, for multiplication, what you do is you add the exponents, multiply the mantissas. Similarly, for division, you subtract the exponents and then divide the mantissas. After that, if you need to normalize, right? So this is the normal step that you need to do. If the mantissa is too small, so you have an underflow, you shift left and you decrement e, so the exponent. If the mantissa is too large, you shift right and increment e, because you always want to have a leading 1 bit for normalization purposes. The next thing that you need to do if you do, for example, multiplication or something, you need to do rounding. If you multiply, for example, two mantissas, you end up with a number that is with a sequence of bits that is longer than what you actually can represent. So you need to map that back to the initial length of the floating point number that you can represent. So you need to apply some kind of rounding. In IEEE 754, which is the floating point standard, this works with something called the parity bits, the guard bits, the round bits, as well as the sticky bits. So if you're in single precision floating point, everything up until the parity bit would be 32 bits. Actually 23, because this is only the mantissa. Then everything after, the first bit after is the guard bit, the second bit is the round bit, and the rest of them are the sticky bit. Are the sticky bits. The sticky bit itself is a logical OR of all the bits that come after the round bit. And then what you see on the bottom is the actual kind of like rounding that you need to do, right? So this Boolean formula determines in which direction you round. And the rounding rule that is the most common in 99.9% of the cases is round to nearest ties to even, which means you round to the nearest number, and if you have a tie, so if you have, for example, 2.5, you round to the nearest even number, which in this case would be 2. Right, and then the last case that you need to do is you need to handle the edge cases. So if you have some multiplication or you have division and you want to divide by 0, that also needs to be handled in your floating point representation. So we also need to handle that in circuit. So to give you a quick overview of how this actually looks like and to make it a little bit more intuitive of the actual representation of numbers that you can do, you can represent zeros, which is basically the all zeros vector of exponent as well as mantissa. You can represent subnormal numbers, which is when the exponent is 0 and the mantissa is something that is not 0. You can represent normal numbers, which are in the range 1 to 2 to the power of e minus 2, where the exponent is everything but 0, all zeros or all ones, and the mantissa is anything from 1 to all ones. And then you can also represent infinites and not numbers. Infinites and not numbers are reserved where the exponent is all ones, the mantissa is 0, or the mantissa is something that is not 0 for not a number. Okay, so now that you know what you have to do in arithmetic if you want to do a multiplication, which is essentially the operations on exponent, mantissa, normalization, rounding, as well as handling the edge cases, and you know the representation of the numbers, let's talk about how to actually encode this in circuit in a zero knowledge proof. Good, so there's essentially two potential ways you can do this. I assume that most of you are familiar with the kind of design spectrum here. You either can do it with tailored circuits, so you really design the arithmetic circuit and then take it from there, or you use universal circuit and universal circuits in a zero knowledge virtual machine and support basically the instruction sets that you need to support floating point numbers, which for RISC-V would be something that is called the F extension, right? In this work, we work over tailored circuits. So on the bottom left, you can see the general way of how you encode encode a circuit. So you compile to a constraint system, you have the backend handles setup, prover and verifier, and then you do the witness generation. What we're going to talk about in this talk mainly is just like how to set up the circuit that then compiles to the constraint system to minimize the number of constraints, right? Good. So given that we're operating in the circuit optimization framework, there's certain tools of optimization that are known and that we can use. What we use in this work mainly are one non-deterministic advice, or something that is also called a hint, as well as lookup arguments. So just briefly for you to know, what is non-deterministic advice? Non-deterministic advice, this is very simply exemplified at the case of the square root example. If you want to compute a square root in circuits, what you would naively do is you take an algorithm that already exists to compare the square root, right? In literature, this is Newton's algorithm, which is basically an iterative algorithm that approaches the square root of a certain number. Now, if you want to do this in an arithmetic circuit, such as shown on the right, this blows up the arithmetic circuit in the number of constraints, because you basically need to flatten the whole loop that you're trying to do in approaching the actual number of the square root. So what can a hint do? In a hint, what you can do is you can provide the result, right, the square root itself, and the actual input, so x in this case, and then you just do one multiplication, you multiply the square root with itself and check that it's equivalent to the other input that you give, which basically ensures that you have the square roots of that number that you're trying to give the square root of. Good, that is one optimization. The other optimization is lookup arguments. For lookup arguments, you essentially have a table and a set of queries. And what you want to do is you want to ensure that the queries are in the table. How can that help? For example, if you want to do a constant size range check, such as 0 to 2 to the power of v, you could either do in-circuit decomposition of bits, or you provide the bits, in this case v0 to whatever, however many bits long the actual value is. You provide that as a hint, and then you enforce that the bits appended to each other are equivalent to the actual number, and all the bits are in the lookup table. Good, so these are the optimizations that we use that are in general applicable to any kind of circuit that you have. Now, additionally, we adapt the representation of floating point numbers such that we can handle them in circuit more efficiently. So as you heard before, you need to treat subnormal and normal numbers differently. What we do is we let the exponent essentially underflow by shifting the mantissa d bits to the left until we have a leading implicit 1, and subtracting that from the exponent. We expand normal numbers to simplify computations by taking the implicit 1 bit and making it explicit, and operating over an unbiased exponent, so we also don't have to handle the bias. So for every number that goes into the circuit, we represent it in unbiased form. And for nans, we do not treat them separately, but we actually unify them by making the mantissa all zeros in our computations. Right, so let me show you how this actually looks. If you actually, so this is the circuit for multiplication that you actually do in the zero knowledge floating point implementation. What you simply do is you add the exponents, you multiply the mantissa. In this case, because we have subnormal and normal numbers unified, we need to account for that, right? Because we did that in the previous step in a different representation, we also need to ensure that the result is in the correct number range. So, so we have the mantissa is always in the range 2 to the power of 2m to 2 to the power of 2m plus 2, as the mantissa of alpha and mantissa of beta is in the range 2 to the power of m to the power of m plus 1. If we now want to normalize, what we can do is we can only check basically whether the most significant bit, so the 2m plus 1th bit of m, is 0 or 1. So m always either has 2m or 2m plus 1 bits. So you do not shift left, so you do not normalize because it's already normalized if the most significant bit is 0, and you left shift by 1 if the most significant bit is 1. Yeah, so we use, for example, the hint here, as well as range checks. And we need to enforce, of course, that the bit that we provide is actually binary, and also enforce the correct range. Yeah, And then additionally, we need to do rounding for the mantissa to cut it into the right range. In this case, either a single precision or double precision floating point, and handle the edge cases accordingly. Yeah. Cool. So this was a very brief overview of how this actually looks in circuits. Talking about everything would be a huge blow up of everything. Yeah, so there's a lot more things to do. You need to do the adapted rounding to also account for subnormal is normal by treating them in a unified fashion. In the circuits, you need to do the implementation of optimized integer operations. So you need absolute values, maximum and minimum values, as well as left shift and right shift, which are very important because you shift basically all the time the mantissa. And you also need to do the rest of the floating point operations. Right now what you saw was only the multiplication. You also need to do addition, subtraction, multiplication, division, square roots, and the edge cases. Good. So now we can handle the actual applications. So projecting onto a sphere. Here you can see the algorithm that we extracted from the Uber software implementation. Essentially what you do, you see this is the baseline algorithm. You have a latitude, a longitude, and a resolution, and what comes out is the IJK coordinates. I'm not going to go into what is the actual transformation, but you'll see what the problem here is in a second. So in each of these steps, you have trigonometric transformations, right? So you need to apply sine, cosine extensively in a number of these steps, which again is very, very expensive because these are iterative approximations, right? So ideally, we want to get rid of them. So we want to optimize the circuit. What you can see here is the optimized circuit that does not have a single trigonometric relation. So we do not need sine, cosine, or tan at all. What do we do is basically we use hints in kind of like a fashion that makes it, that enables us to compute the right numbers only by applying a square root. And then successively we use standard trigonometric relations that probably everyone here has learned in their high school education to essentially represent every calculation in a non-trigonometric way. Yeah. So as you can see here, on the left is the unoptimized implementation, and on the right is the optimized implementation that has basically been optimized with trigonometric identities to get rid of all of the trigonometric relations. What you can see on the right, wherever there's a trigonometric relation still, that is basically a constant. Yeah. Okay, so how can we ensure that everything is correct? In the beginning, I talked about the resolution and approaching the boundary of the hexagon in a logarithmic fashion, which you can see here. Every resolution, 11, 12, 13, 14, and 15, has basically around like 10 test cases, and each hexagon, 11, 12, 13, 14, and 15, is always kind of like decreasing in size. You can see for P6, which is a fixed point implementation, you have a lot of errors, and for single precision, as well as double precision, you're basically fine, besides like for 15. For the floating point implementation, we ensure that everything is correct by testing it with the Berkeley test float implementation. So in this case, we achieve equivalence with the IEEE standard. How costly is all of this actually? So we have two parts, native constraints and lookup constraints. On the bottom left, you see the equation that you need to check for the lookup constraints. The good thing here is on the right-hand side, so you need to do three things: calculate the left-hand side, check the equality, and calculate the right-hand side. The second and third are actually constant. So this amortizes the more multiplications, floating point multiplications you actually have in your circuit, right? So to briefly give you a gist of the rights, what we have, for example, for FP32, which is single precision floating point implementation, you get down to 64 constraints per single multiplication as soon as you have around 2 to the power of 9 multiplications in your circuit, right? For the evaluation of our application, zero-knowledge location privacy, I mentioned in the beginning, you want to calculate the distance for peer-to-peer proximity testing as well. For that, we can test the proximity with a single proof up to. So you receive, like, as a verifier 400 proofs, and you can check all of them in like less than a second. And on the prover side, we have a prover time of also less than a second and roughly 20,000 constraints for single precision floating point implementation, and roughly around 50 to 80,000 constraints for double precision floating point implementation. Yeah, and yeah. So remaining challenge is still location authenticity. As you might know or might have realized, there is no assurance of the actual authenticity of the input latitude and longitude, which is still problematic. We think this is a very nice future research direction where you can either figure out how to do it with satellites, with TLS Notary, or with some kind of like hardware processing devices, so TEEs. And we also think that this would be fun to do with IVC, so you can do something like write-share calculation across, yeah, a similar kind of like Uber algorithm where you could apply incrementally verifiable computation. Yeah, and privacy-preserving validated geolocation is also very great. Cool. Yeah, now you can use floating point arithmetic in your custom circuits. Yeah, happy to take any questions. Thank you.
All right, we got one question. We have time for one question.
What do you estimate the amount of work that needs to be done to extend this floating point unit into any of the ZK VMs that exist?
I've actually worked a bit on this in the summer, and this is kind of like still upcoming work. So what you need to do is you would need to figure out how to model basically model the there's the F extension already, right, for RISC-V, which is already implemented in plain. So now you have to figure out, I worked on this for Jolt, so we tried to figure out how to represent this as multilinear extensions to use it with the lasso lookup argument, right, to make it amenable to proving with Jolt, similar to the base instruction set, which was basically the initial contribution of Jolt, base instruction set plus M extension. Yeah, and the F extension would basically follow a similar paradigm, but if you want to have IEEE 754 compliance, you need to implement a lot of branching, right? And I think there's a lot of optimization here. The question is, do you need IEEE 754 compliance for every single application? I guess not. So yeah, I think a lot of these applications could also benefit from cutting out a lot of constraints that are only relevant for edge cases, right? Which are still used in our implementation because we wanted to achieve that. Yeah.
Thank you very much, Jens.
Thank you.